Hello and welcome to this second feature engineering lecture in this course Master in Artificial Intelligence. So in this lecture we'll continue to talk about how to engineer new features and transform existing features, and we have laid out an overview of the process and we will take you forward in that process. So the next step, you have the first two steps we covered in the last lecture of understanding the problem and data and performing EDA, kind of quickly summarized there. And we now need to look at how to how to engineer new features or transform existing features, how to figure out the variables that you don't know, and that's the most important step. To figure out what you don't know is the most difficult part, or transform existing feature. And let's look at some of the techniques that you can use in this lecture. So one of the techniques that you use to transform data is what is called one-hot coding, and this is typically useful for the categorical variable, where as you see here, the gender is the category and the output is either male or female. So the gender is a categorical variable. So you convert that categorical variable into binary indicators in using the one-hot coding, in which each one is either 1 or 0 in the two categories, male and female. Now this is a transformation of the variable to make it suitable for processing. The second one is called feature scaling, in which you scale the numerical features. We talked about categorical, now let's talk about the numerical. Now, these different numerical features could be of different range. Example, one could be 1 to million range and one could be 1 to 100 range. Now, if you leave it as it is, the 1 to million variable might dominate. So you need to scale the numerical features to similar range to prevent dominance by such features that are large in number. So you bring it down to the same scale, right? Now, there's another thing you can do to transform data is to do feature normalization, in which it's a form of a scaling that we just talked about, in which you use the mean, you reduce the feature data to with a zero mean and unit variance, and that improves the model convergence. Now, what does a mean normalization mean? So, supposing you have data x1 and x2 here. X1 is the size of the room from which is ranging from 1000 to 2000, and bedrooms from 2 to 5, right? So, in that case, what you do, that's the variable x1 and x2. Now, in this, what you replace, you create a new variable called xi, in which you replace x1 and x2 with x1 minus the mean divided by the variation. Now, variation could be a standard deviation or it could be a simply a range. So you see the calculation, come back and take a look at it, and that's how you can do a normalization. So you're normalizing data to a zero mean and unit variance. So subtract mean, divide by the variance, and you get this whole thing done. Another thing that you do in visual features is aggregate or combine multiple related features to create a new informative feature. Now, if you see the if its initial image consists of the top left, it will generate two feature maps, feature map 1 and feature map 2. Now, you could and the best way to use this will be to aggregate feature map 1 and feature map 2 in a feature space, and that will give you a third feature, and then you can map them on M1, M2, M3 regions. So three maps you could create using the two feature maps. Now, another technique that you can use, very useful and powerful technique, is polynomial features. Now, polynomial means, when you use the output variable and input variable, the output variable y is a function of x1, x2, x3, the independent variable, the factors, the features, so whatever we are calling. Now, the polynomial means normally if it is a linear function, then the output, the y, is a linear function. It is a constant multiplied by x plus a constant again, right? Y is 5x plus 10, kind of a thing, example. Now, in polynomial, the multiplication factor of the x1, x2, x3 is not a constant. It is It is a constant, but at the same time there are higher orders of x1, x2 that come into the play. So how can you generate these polynomial features to capture a nonlinear relationship between variables? Now, this is a technique used to capture the non-linear relationship. A linear relationship will show an output on the vertical scale versus input on the horizontal scale, a line, straight line going across. Okay, and here you see these are curved of different kind in degree 3, degree 4, degree 5, and you see different types of curves that are available, and that's what is called a non-linear relationship. So you can generate these polynomial features using some algorithms which can create new features that are polynomial combinations of the original features. Now, how can you generate these polynomial features effectively? Let's take a look at that. So what you do is you start with importing the library. Yeah, if you import the library, uh, uh, you will typically need libraries such as NumPy, Pandas, and scikit-learn. Then you prepare the data. Then you load to prepare your data set. Ensure that the data set contains the features you want to use to generate the polynomial features for. So if you want to if you have 10 parameters and out of which you want to use 3, make sure that you have data for that. Then you instantiate the polynomial feature, in which you create an instance of the polynomial feature class from scikit-learn, specify the degree of the polynomial you want to generate, whether it is 2, 3, 4 or 5 or 6 or 10. Then you fit and transform the data. Fit the polynomial feature instance to the data and transform the original feature into polynomial features. Then you convert into the transform polynomial features into data frame for easier manipulation and analysis, and then you review the resulting data frame to see the generated polynomial feature, right? And then finally you are ready to use in modeling once you find that your polynomial function is representing well the data that you wanted, and you use this generated polynomial feature along with the original features for modeling. Remember the word original features. So you're trying to generate more features using the combination of your existing features or factors. Uh, More things you need to do is to then do the feature interaction. One of the techniques to create more feature is to do feature interaction, in which you create new features by combining or interacting existing feature to capture complex relationship. Polynomial function was one of those. Now, how do you do that in general? You identify the relevant features. You start by identifying the existing features in data set that you want to combine or interact with to create new features. Then you consider factors that may have meaningful relationship or interaction with each other based on the domain knowledge or maybe some kind of intuition itself. Then you combine these features, two or more existing features, to create new composite feature that capture interaction or relationship between them. And so it's all play, it's all hypothesizing here. And the common techniques for use for this feature combination include addition, subtraction, multiplication, division, or concatenation of the feature values. Then you get into feature interactions. You create new features by interacting or combining existing feature in a non-linear way to capture the more complex relationship. The examples of feature interaction include like the polynomial features we talked about, cross products, or the transformation that amplify or diminish the effect of existing feature. Logarithmic is another way. Then you get into what is called feature engineering, in which you apply the domain knowledge and intuition to engineer new feature. Feature engineering is primarily figuring out getting new features that may capture important interactions or relationship of the data. And there you experiment with different feature combinations and transformations of features to identify the most uh, important, informative, and predictive features. And you then get into evaluation of and validation to basically to see their effectiveness in improving model performance using techniques such as cross-validation or holdout validation, and you monitor the impact of new features on model performance and adjust the needed adjust as needed on the validation results. And finally, you iterate and experiment with different feature combinations, interactions, and transformations to optimize your model performance, and continuously evaluate and iterate and refine feature engineering strategies based on the feedback from the model evaluation and the domain expertise. So by following these steps, you can effectively create new features, and that is the purpose of future engineering, right? Where you either use your intuition or domain knowledge to find new features, or you combine or interact existing features to capture complex relationship in the data, which ultimately improves the performance of your machine learning models. Then there another technique that you can use is the domain specific features. Now in domain specific features, what you do is it is based on the domain knowledge or expert insights to capture the relevant information, uh, and this involves leveraging your understanding of the problem domain to create new features that capture relevant information or patterns in data. And the question then is, okay, so how can I do this domain specific feature engineering? So you need to start with understanding the problem domain, get a good understanding of the problem that you are trying to solve and the domain in which it exists, and get familiar with the terminology, concepts, and key factors that influence the problem. Talk to experts, collaborate with domain experts, subject matter specialists, and stakeholders who have the knowledge and expertise in this field. Sit down and have discussions, interviews, and workshops to gather insights, identify important variables, and understand the underlying the dynamics of the problem. And this is a kind of a brainstorming that you do. Then you identify key variables, factors, or features that are known to influence the target variable or the output, right? Based on the domain knowledge and experts' insights and discussion with them, you consider both quantitative and qualitative factors, both categorical, numerical, that may be relevant to the problem. And then you get into feature extraction from raw data or existing variable that capture relevant information or patterns identified through domain knowledge. You create new features and transformation that encode domain specific insights or relationship in the data, and finally encode categorical variables or quantitative features using domain specific encoding techniques that preserve their meaning and relationships on the target variable. Continue to consider techniques such as one hot coding, ordinal coding, target coding, or frequency encoding, depending on the nature of the problem and the data. Also, you can use temporal features or time-related variable that capture trends, seasonality, or periodic patterns of the data. You can also use features like timestamp, time tag, moving average, or time-based aggregations to capture temporal dynamics. Uh, if applicable, include geospatial features or location-based variables, right? That captures spatial relationship or geographical characteristic of the data. Now, this could be things like distance to key location, clustering based on geographical proximity, or area-based statistics. Apply domain-specific transformations of or pre-processing techniques to data to highlight relevant information or to and also suppress noises. Consider techniques like logarithmic transformations, scaling, normalization, and domain-specific filters. Get into iteration and validation through steps that you saw here from 3 to 8, experimenting with different features, engineering strategies based on domain knowledge and expert insights. Validate the effectiveness of engineered features using cross-validation, holdout validation, or domain-specific evaluation criteria. And finally, collaborate with the domain experts. Continue to maintain an open communication with domain experts and stakeholders throughout the feature engineering process. Solicit feedback, validate assumptions, and adjust feature engineering strategies based on the domain expertise and real life strategies. So, by leveraging domain knowledge and expert insights to engineer feature, you can create informative, relevant, and meaningful variables that enhance the predictive power and interpretability of your machine learning models, ultimately improving the performance and utility in the real world applications. So, having looked at how to engineer features, what will we do now? We will come down to narrowing from this large set of features, which could be in hundreds or tens or dozens, to select a subset of the most relevant features. So, we have done the brainstorming, gone and looked at all possible features, and now we will select some of the relevant features. So thank you so much for watching this second feature engineering lecture in this course, Master in Artificial Intelligence. I hope you continue to learn new things, continue to enjoy, and I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions. I'll be happy to answer a question, and also download the PDF file to take a look at anything that is of specific interest to you, specifically that normalization slide.